Hey friends, it's Ben again. This is a video for the, Calc 3 class. We are looking at applications, specifically applications that pertain to doing double and triple integrals. So I'm not going to do just bunches and bunches of these because I suspect that Don is going to have some kick butt stuff on his video, and I just can't compete. So anyway, though, the main thing that we're going to think about with these applications is stuff where you've got some definable function that takes place in 2 dimensions, 3 dimensions, whatever, and that you're doing some kind of a summation over it. Okay. The typical thing to talk about is figuring out the mass of an object, especially the mass of an object that has a variable density. If it has a variable density, then you can think about at each point taking a little element of volume around it where the density is roughly constant in that little element, and saying, well, that's dV and that's your rho. They tend to use a rho for density. I'm going to use a delta for density. Okay. I think the reason should be obvious, but just in case it's not, we used rho to mean something else, distance from the origin. So anyway, you take that delta times that dV, and that's a little bitty piece of mass. And then when you add them all up, and integrals are your tool to add up an infinite number of things. So infinite sums, sort of the stuff that we started the semester with. So, all right. So assuming that everything works the way it's supposed to, I'm going to launch into some examples here with the iPad. And that would be a no. Things are not going to work correctly. Pausing. Let me try this again. Okay. Let me try the third time. It would be super nice if there was some way to monitor this without having to just try it over and over again, hoping that eventually it would work. Eventually it worked. Great. I have no idea what I said to you the several minutes ago when I started trying to connect here, but we're talking about applications. So the specific application we're going to look at here is to find the centroid of the right circular cylinder that has a height of h and a radius of r. So with regard to that, there's several things to unpack. The first is, what the heck is a centroid? Well, a centroid is a center of mass, which you might say, gosh, you didn't help me a bit there, Ben. So a center of mass is a point in the object where you can treat the entire object as though it were a point mass at that place. It's used in a lot of things to try to simplify calculations. For example, if you can figure out where the center of mass of an object is and you have the object sitting on a base, then as long as the center of mass is above that base, then the object is going to be relatively stable. The closer that you have the center of mass to the edge of that base, the less stable it will tend to be. So, all right. So anyway, here though, in particular, the word centroid means assume you have a constant density for this object. So the density, I mentioned to you all that I will use a delta to stand for density. So that's going to appear in the problem here. So we need to find 3 coordinates for the center of mass, the x bar, the y bar, and the z bar. So if we think about um, our wow, hey folks, how about if I use the word I actually mean on here, cone. Okay, so if we're looking at this cone here, we're going to set it on the XY plane so that the base right underneath the vertex is going to be at the origin, okay? So from radial symmetry, or maybe azimuthal symmetry, as Don put it one day, this cone should have the X and Y coordinates of its center of mass just being 0. If we had something that did not have constant density, then we'd have to worry about it a little more, okay? But all we have to figure out then is going to be the, where the heck did I write it down here? The Z bar. So that is going to be the Z coordinate of the center of mass. So in order to do that, you make use of a formula, which I have not written down here anywhere, but it is that Z bar is going to be equal to the moment about the XY plane, then divided by the mass of the object, okay? So that is, in fact, what we are calculating here at the very end. And so maybe I should go ahead and put this in here where it'd be easier to see. All right, so for our purposes though, we're going to have to figure out this m sub xy. And what m sub xy essentially does is to take the distance from the xy plane, z, and put it in the middle of this. In a sense, you could think about this as the weighted average of the z values. So because you have much more of the cone down here towards the base than you do up here at the top, that means that the stuff at the base is going to count a lot more. And when we're averaging these z values, it's going to count in a lot more on the integral. And so consequently, you will get something that is much closer to the base than it is to the top, all right? So we're saying delta is the density and it's some constant. That means we can factor it out to the beginning. And then we have to set up the integral across this cone. Now we did a cone, something or another with a cone, I think the volume of it in a previous section. And the thing that you're wanting to do with that is essentially to think about living in the RZ plane here, and you want to get a straight line, which you could then rotate around 360 degrees in order to create that cone. So making that straight line, we need its height up there to turn out to be h, and we need its radius to turn out to be r. So then we can just apply the point slope formula and stuff, and we can actually get an equation for that. And that is where this h times 1 minus little r over big R actually came from. If you notice, when you plug in little r equals 0, you get h. When you plug in little r equals big R, you get 0, right? And those are what we want out of that line. All right, anyway though, once you've gotten to that point of it, it's really just a matter of doing the integration. We're integrating with respect to z here, so we'll get the 1/2 z squared. And when you do that, you need to plug in that top limit and then minus plug in the bottom limit. So the 1/2 appears here. Oh, also notice that we're integrating 0 to 2 pi, and there aren't any thetas appearing in the actual integrand. So that means that we can just go ahead and put that 2 pi out front along with the delta. And now we have a somewhat yucky looking thing to work with there. But if you notice, we can pull an h squared out of it, and then we can just square out that 1 minus little r over big R and have this yucky looking thing here. But we're integrating with respect to little r, so that's not too bad. You get a little r and then a 1/2 little r squared, but you had a 2 in that, so that works out. And then a 1/3 little r cubed. And all you have to do now is to plug in the big R and then the 0, because everything in there has a factor of little r in it. Then the zeros will make things vanish. But when you do the algebra of it, you should end up with 1/3 pi big R h squared delta. Okay. Now, insofar as the mass that we're dividing out on this other piece of the formula here, that mass is just going to be the density times the volume, right? And so you just take our formula, 1/3 pi r squared h, which you should all know from whenever you learned those things, and multiply it by a delta. And then to get the z bar, we just have to divide these things. And so that top up there, you end up with the 1/3 pi r h squared delta, and on the bottom, the 1/3 pi r squared h delta. And bunches of stuff canceled. The deltas go, one of the h's goes, one of the r's goes, the pi's, the 1/3s, boom, boom, boom. All we're left with is h divided by r. So depending on what the height is and depending on what the radius is, that's going to decide where the z coordinate ends up being for your cone. All right, cool. So then another example here, we've got a solid that's going to be bounded by z equals 0 and z equals 16 minus x squared minus y squared. So if you're looking at this guy over here, this part up here is going to be given by the 16 minus x squared minus y squared. And then the bottom of it, of course, is going to be given by the z equals 0. So we're getting this piece of information here. We've got a density 1 plus z. I just wanted to make sure that we did an example where we actually had to deal with a z, with a density that was not just constant. So I made up something. Since you've been in this class for a while, you know when I make up something off the top of my head, it always ends up being really miserably hard to do the integration. So I made up something that wasn't too bad, and we'll just follow it through. Okay. All right, so we're going to be doing the moment of inertia, and that's just defined to be that you're taking the square of the distance from the axis you're taking the moment about. And so the square of that distance is going to be x squared plus y squared. Okay. If you didn't have the square, then it would just be the square root of that. But so because we've got an x squared plus y squared, and this thing here has a circle as a base, that tells us that we probably want to do cylindrical coordinates. So we'll have r squared, 1 plus z for the delta, and then the r to go with the dz dr d theta. Okay. And so setting up the integration, you can see that it goes all the way around. So you'll have the 0 to 2 pi. And then on the inner limit of integration here, you're going to want to think about coming up towards the region. You hit the z equals 0 to enter the region, and then you hit the z equals 16 minus x squared minus y squared to leave the region. And then that gives you your two limits. So 0 and 16 minus r squared. Okay. And then the place where z equals 0 meets z equals 16 minus r squared is going to be a circle in the plane. And if you set those equal and solve, you know that you're going to get r equals 4. So for doing the r portion of this integration, we start at the center and go out. That's the direction that r increases, so the dr. So we'll go from 0 to 4, because 4 is the radius there. So once we've got the integral all set up there, all that's left is to just integrate it. Remember here, we're starting with the z's. So we get z plus 1/2 z squared. We have to plug in the 16 minus r squared and the 0. Having 16 minus r squared for z is not bad, but having it for the z squared is a little bit of a mess. So I skipped the algebra here because I didn't think you wanted to watch me do that. But assuming that I did all of that algebra right, then we end up with this 144 minus 17r squared plus 1/2 r to the fourth. And we're going to multiply that by an r cubed. And then we have to integrate that with respect to r. And so 144 divided by 4, 17 divided by 6, and 1 divided by, I'm sorry, 1/2, was it? Yeah, 1/2 divided by 8. Raise all the powers, go 0 to 4, and you get an intolerably huge number, okay? And so I started to put it as a fraction, but it was going to be over 10,000 something pi, then over 3. And when you work it out, it's going to be approximately 10,723.3 something or other. Okay. So what do you use moments of inertia for? Ask Don that question. I've got to admit, to me, they're things we have to calculate. And so, all right. So here's something I will often say to y'all that I am not a statistician, and statistics don't really excite me, but probability I think is kind of neat. So we talk a bit, and you can look in the text about this, we talk a little bit about probability distributions, and especially joint probability distributions. So these are functions of x and y, and if you integrate them across the entire area where they are non-zero at, then the answer needs to turn out to be 1. So this particular example here, we're going to have the joint density function for x and y, let me say something about that in a second, to be c times xy, with the c undetermined right now, but the x and the y, we're allowing both of those to vary between 0 and 2, okay? So now a quick word about the capital X and capital Y. This is super weird sounding, but we have these things that we refer to as random variables. And we like to use a capital letter to stand for the random variable when you have not had an observation of it yet. When you make an observation, they usually use a lowercase letter to stand for whatever the observation was. So if you're rolling a bunch of dice and you get your roll could be 1 to 6, they'll say capital X referring to a roll, and then they will do calculations with the various little x's. So little x equal 1, little x equal 2, little x equal 3. So that's the kind of thing that's going on there. If it bugs you, just ignore it. Just use lowercase x and lowercase y. That's what you've always been doing. And the theoretical difference in it just isn't worth the headache unless it's something you actually want to study, okay? All right, so the first thing here is that we want this to be a valid probability distribution. So we need to find a C value that makes it valid. So we're going to take a look here, and I guess I should have drawn a bigger one of these to start off with. But we're going to take a look here at the region that we have a we're going to look at the region. Wow, I can't draw. For which the probability is non-zero. Okay, and so that's going to be represented here with this part on that. And so all we're going to do is to do the calculation of the total probability by integrating across that region. Now, that's not a super hard integral to do, right? But you just take that probability function and you integrate it across your region. In this case, the region was square. In some other case, it'll be something different. But you can factor the c out, and you can then integrate either the x or the y first. I mean, actually, you could have just separated that out into two integrals, right? And so you would end up getting 1/2 out of both of those integrals. Am I saying the right thing? No, I'm totally not. You would end up out of each of those integrals getting a 2. And so at the end, you would end up with a value of 4c, okay? And we know that 4c has to be 1 because that's part of our definition of a probability distribution. The integral across the entire support, the area where it's non-zero, needs to turn out to be 1. So we set it equal to 1, we divide, find out c needed to be 1/4. Then we use that in the rest of the problem, okay? All right, so the next piece of it says, let's go through and find out what is the probability that x and y are both less than 1. So when you're given that, then you have to think about drawing the region where that occurs. So we know that our support is 0 to 2 on both x and y, so the big square there. But this little square is going to be the area where we've got x being less than or equal to 1 and y being less than or equal to 1. So it's a rectangle, so it's super easy to set up the integration. You've got integral 0 to 1, integral 0 to 1, 1/4 xy dy dx. If you wanted to do dx dy, would have been fine. So in any case though, pull the 1/4 out to the front, start doing your integrating, and you come down at the end to getting 1/16. Boom. So that is the probability of choosing an x value and a y value both being less than 1. Okay. All right. So then the next problem here is finding the probability that the x plus y is going to be less than or equal to 2. So I go ahead and draw the line where x plus y equals 2, and it happens to bisect my region. I could very well have had something, where the line that was cutting it was someplace else, but just this particular setup ended up bisecting the region, which your intuition probably tells you, aha, probability would be 1/2, because you can see that, yeah. But we had seen just a second ago that the probability of this little quarter turned out to only be 1/16. The thing that's going on is the stuff that's up in this corner is much more heavily weighted. So we're actually going to get an answer here that's significantly less than 1/2. So anyway, you have this region that we've colored in here, and you just have to set up your integral, the 1/4 xy, and then your y values increase going across there, and they enter the region at y equals 0, exit at y equals 2 minus x. And then the x values go all the way across from 0 to 2, and now we've got our integral set up. Once you get your integral set up, you just go to town with integrating. Pretty much the same integration that you did previously. It gets a little bit more interesting here because of the fact that you've got the 2 minus x being squared, and then you have to multiply it out and then integrate that. But here at the end, unless I made an arithmetic error, we should end up with a probability of 1/6, okay? Which again is significantly less than the 1/2 that our intuition might have suggested to us. So, all right, one more. Okay, so this time let's let the x and y have a joint PDF, which is given to us by f of xy equals xy. So it's pretty much the same thing. It's just, a multiple of it. But I purposely here set things up so that the y values went 0 to 2. Nope. I drew the opposite of what I meant to draw. Oh, I'm sorry, folks. So bear with me because I can't bear to just let this go. If the x's are what's going from 0 to 2 instead of the y's, then that means that we should Yeah. Pardon me for just a second here as I try to, nope, nope, nope. Okay, so I'm trying to color this in here as best as I can. All right. So that's our region that we got there. And with those setups on it. So what we're trying to do in this case is to find the expected value of the X or the Y. So when you're doing expected values, the thing that you do is to take whatever you're doing the expected value of, in this case, the expected value of the X, but it could be X squared, it could be X plus Y, whatever it happens to be, you're going to just come up here and put that into this, this integral here and multiply it by the density. Notice that that looks exactly like what we did with the moments a minute ago. Okay, you had something that was a function and you multiplied it by a density, and then you took the integral across the whole region. It's exactly the same thing. It's just that now we have the abstraction that somehow it represents a probability or something. So here, the X bar that we're talking about, I could also refer to it as the expected value of X. And I just come along here and plug that in, and then I have to integrate across the region. And you'll notice that we have X's and Y's that we can separate out. And the region itself is a rectangle. So that means we can do the integral 0 to 2 of x squared dx and 0 to 1 of y dy. And when we do that, we end up with 8/3 times 1/2, and that gets us 4/3. So the expected value of X, the kind of average of it, is then going to turn out to be somewhere about here-ish. So more than halfway, because again, there's a heavier weight to put on stuff that's to the right, okay? And then similarly, we come along here and try to figure out the average for our Y, and we just put Y times the probability density function, and we integrate across the region. We've got two integrals to do, just like before, but they're quick intervals, or quick integrals to do, right? So we get 2 and we get 1/3. And so we end up getting 2/3 out of this. And so that means that the average for the Y's is going to be 2/3 of the way up there. So a little bit more than 1/2. So our center, so to speak, center of mass for this probability distribution ends up being higher and to the right from the center, okay? And this is an important thing for you all to realize on probability distributions is they're not all uniform, okay? If I talk about throwing dice, a die, I expect to have a uniform distribution, the same probability for each die, okay? But, sorry, for each number on the die. However, if I throw 2 dice and add the results together, suddenly the distribution I've got is not uniform. It's much less likely for you to roll a 2 than it is for you to roll a 7, because there's only one way to make the 2 and there's 6 ways to make the 7, okay? So in any case, you need to bear in mind that probability distributions and data, if you don't know what the distribution is going to be, you can't just say, aha, it'll be the middle, the halfway between the high and the low. It's just, data doesn't tend to work out that way, okay? All right, anyway, though, that's a couple of things about probability, a couple of things about moments. And like I say, watch Don's video, because I expect there to be lasers. Oh, man, if he uses lasers, I'm totally gonna lose it. So, all right, see you all in class.